everyone! In this video, we are going to be talking about properties and characteristics of gases. You guys can be following along on page 3 of your packet of fun. So it looks like this. And we're going to first go over the kinetic molecular theory, then some properties of gases, and then we'll be going over pressure, and I will also go over a conversion with you guys. So the kinetic molecular theory of matter. Basically, you guys know what the word kinetic means. It's the energy that involves speed. So the faster things move versus the slower things are moving. So it basically states that all matter is made of constantly moving particles. And here are some of the various things that the kinetic molecular theory has as well. We're going to kind of go over some of these together because I think that they're easier to explain if we group them up together. For instance, let's just read through the first 3 here. Gas particles have insignificant volume. Gas particles are very far apart relative to their size, and there are no attractive or repulsive forces between particles or particles in the walls of the container. Actually, we're going to go through all of it. It just makes more sense. So the fourth one says gas particles are in constant random motion. 5 states gas particles travel in straight line paths until they collide with each other or the walls of the container. And gases have perfectly elastic collisions. So let's go back to the virtual lab that you guys did. If you take a look here, the actual size of the gas particles are very insignificant for the amount of space that they're consuming. They're very, very small and they're very, very far apart from each other. You can see that they're constantly moving. You can see that when they hit each other, they keep on going. When they hit the walls of the container, they keep on going. That's what it means to be perfectly elastic. Imagine bouncing a bouncy ball and then it never stops bouncing. That's an elastic collision, and gases behave like that. Now, let's talk. Let me go back and make sure I'm following along properly. We'll just talk about some properties of gases next. You guys can be filling in that area of your packet, so that area on the center of the page there as I go through this. So some properties of a gas is that they're fluid. So for instance, we've been using a lot of Lysol recently, or maybe you have an air freshener in your house. So what it means when gases are fluid is that they are going to flow and fill whatever container that they're in. They move around and they end up filling the space. That leads into our second one, is that they completely fill a container. So if we were to take a look at this again, if I make the space smaller, the gases still fill this particular container. If I make this space larger, they still fill a container. Gases have a low density. So remember that density equals mass divided by volume. Since volume is insignificant, okay, so the amount of space that gases take up is not very aligned with the amount of space that each particle takes up. So, or I guess the space that it consumes. Because they're moving around and they have lots of space to move around, it makes the volume larger. But the mass of the actual particles is very few since they're so spread out. Okay, so the mass divided by volume is very low. And that's what it means when it says it has a low density. Okay. It says here that gases are highly compressible. If we go back to this simulation here, what that means is that we are able to squeeze the amount of space that gases have to consume. Why are they compressible? Because there's a lot of space in between them. So there's an area that can be compressed. Unlike liquids or solids that are already close together, there's no way we can squish them together anymore. But for gases, we can squish them together since they are very spaced out to begin with. And then lastly, gases have pressure. So this is the biggest thing that I hope that you took away from that virtual lab. Pressure is something that's caused by collisions of molecules. When you were doing this lab, we did a collision counter, and the collision counter then ended up changing the pressure. Pressure is basically how often and how much do the gases hit the walls of the container. So the more times it hits the walls of the container, the higher the pressure is going to be. The less times that gases hit the walls of the container, the lower the pressure is going to be. That leads us to this next one, or this next slide. Pressure. Again, if you haven't written it already, pressure is determined by how often walls hit the container. So if you have a high number of collisions, that is going to equal a high pressure. Make sure you have this down and have a good understanding of this. What you see now is I have an equivalence ratio here of the different types of pressures that are out there, the different units of pressures. So kPa stands for kilopascals. mmHg is millimeters of mercury. Torr stands for torr. And ATM stands for atmospheres. I will say the most common one that we will deal with is ATM. Now what you see up top is this little line here. If you haven't already, I do want you to write this down. It says that 101.3 kilopascals is equal to 760 millimeters of mercury, which is equal to 760 torr, which is equal to 1 atmosphere. With that being said, 1 atmosphere is then also equal to 760 mmHg, and 1 atmosphere is equal to 101.3 kPa. 760 mmHg is equal to 760 torr. So you can kind of see how you can manipulate this little number line here, and that it's just one big equivalence ratio. With this, we are going to be doing a couple conversions, but I'm going to first talk to you a little bit about standard temperature and pressure. So in the last unit, we talked about STP and gases that are at STP. Then 22.4 liters is equal to 1 mole of something at STP. So STP stands for standard temperature and pressure. And these are the conditions under which scientists study gases. And what I'd like you guys to write down is what's in this area here. That for temperature, standard temperature is 273 Kelvin, or in Celsius, that is 0 degrees Celsius. Standard pressure is equal to 1 atmosphere. But if you take a look at our line that we just went over, 1 atmosphere is also equal to 760 torr and 101.3 kPa. So if I've ever asked you the standard pressure in kPa, then your answer would be 101.3. If I ever asked you for the standard pressure in torr, then it would be 760. If I asked about atmospheres, well, then it would be 1 atmosphere. So I think you're getting it. All right, I'm going to go over how to go from Celsius to Kelvin, because we are going to be calculating in this unit, and you do need to know how to convert to Kelvin, because the thing is that our thermometers measure in degrees Celsius, but in order to do gas law calculations, it has to be in Kelvin. Okay. Now, in order to get to Kelvin, you just have to add 273. So here's our little formula here to get to it. So Kelvin is equal to whatever degrees you have in Celsius. So say we had 20 degrees Celsius. Kelvin is going to be equal to that 20 degrees plus 273. So 20 degrees Celsius in Kelvin here would be 293 Kelvin.